Welcome to the deep dive. Today we're tackling a really fundamental area for anyone building serious systems. Database replication. Think of this as the core knowledge you need to not just answer interview questions, especially for that senior software engineer role, but to actually design and operate resilient, scalable databases.
Definitely.
We're going to dissect the main approaches to replication, focusing on the crucial trade-offs you need to internalize.
Exactly. For those gearing up for technical interviews, particularly at a senior level, it's not enough to just define these replication methods.
Right.
You need to demonstrate a deep understanding of their implications, the pros, the cons, and how they fit into different architectural scenarios. We'll be diving deep into several key techniques to equip you with that comprehensive perspective.
Okay, let's unpack statement-based replication first. The basic idea is pretty intuitive, right? The primary database, the leader, logs every single write operation, every SQL command that changes data, and ships that log to the secondary database as the followers, which then try to execute those exact same statements. Seems straightforward on the surface.
It does, but the core insight here is that replicating behavior, the SQL statements, rather than, the actual state changes, introduces significant risk of divergence. Consider what happens with non-deterministic functions like and now rand or rand.
Oh, right.
If the leader and followers execute the same insert statement at slightly different times, the recorded timestamp or the generated random number will be different.
Leading to inconsistent data. Yeah, because those functions can produce different outcomes each time they run, the replicated data isn't guaranteed to be identical. And it's not just those obvious examples, is it? What about auto-incrementing columns when you have concurrent transactions?
Precisely. That's another big one. If multiple insert statements are happening at roughly the same time on the leader, the order in which they're logged and subsequently replayed on the followers might not be exactly the same. This can cause the auto-generated IDs to be assigned differently, leading to mismatches in your data relationships.
Yeah, I can see that.
Similarly, if an UP-date statement has a where clause that depends on the current data, well, if the data on the follower isn't an exact mirror at that precise moment of execution, the update might affect a different set of rows, or maybe even no rows at all.
And we also need to think beyond just basic data manipulation, right? What about triggers, stored procedures, or user-defined functions that might have their own hidden side effects?
Those introduce another layer of complexity, absolutely,
Right.
unless these are meticulously designed to be completely deterministic, meaning they produce the exact same outcome in every environment, every single time.
Which is hard.
It's very hard. You face the risk of the followers diverging from the leader due to these non-logged side effects.
I remember reading about attempts to mitigate some of these issues. Like the leader could try to resolve the non-deterministic values before logging the statement, essentially replacing @NOW with the actual timestamp.
That's one workaround, yeah. The leader calculates the value and puts the fixed value in the log.
Okay.
However, trying to anticipate and handle all these edge cases becomes increasingly complex and, frankly, brittle. It adds significant overhead and potential for overlooked scenarios.
Right.
That's why, despite the log size being relatively compact, which is an advantage, the inherent fragility of statement-based replication, just because it depends so much on the exact execution context, makes it unsuitable for most modern applications requiring strong consistency.
Interesting. It's useful to know that this wasn't just a theoretical concern. I understand older versions of MySQL actually use this approach.
They did before version 5.1.
And it might still have niche applications and systems with very strict determinism requirements, like VoltDB maybe.
Possibly, yeah, where transactions have to be deterministic by design. But for general purpose, robust replication, it sounds like we need something more reliable.
Definitely.
Exactly. So now let's shift our focus to a fundamentally different approach. Write-ahead log, or WAL, shipping.
Okay, WAL shipping.
Many modern database systems rely on a write-ahead log for ensuring durability and enabling crash recovery. That's its primary job.
Right, ACID compliance and all that.
Precisely. But the same mechanism can actually be leveraged for replication. How does that work, you think?
So as I understand it, databases, whether they use log-structured storage engines, which are basically all about append-only logs, or more traditional B trees, they first record every single write operation in the WAL before actually applying those changes to the main data files.
Correct. Crucial step.
This WAL is an ordered append-only history of all modifications. So with wall shipping, the leader doesn't just write this log to its local disk, it continuously streams this raw log data over the network to the follower databases.
Precisely. The followers then take this stream of log records and essentially replay all the low-level changes described in the log.
Low-level changes, okay.
Yeah, think byte changes in disk blocks. This allows them to construct an exact bit-for-bit copy of the leader's data structures on disk. PostgreSQL and Oracle are prominent examples of databases that utilize wall shipping.
That makes sense. Because the followers are replaying the very low-level disk operations, it would seem to guarantee a very high degree of consistency, almost a physical copy.
It does offer extremely strong consistency. But there's always a but, right?
That's catch.
The primary limitation stems from the extremely low-level nature of the write-ahead log itself. It contains very fine-grained details about exactly which bytes were modified in which specific disk blocks.
Okay.
This creates a very tight coupling between the replication process and the underlying storage engine of the database, the internal format.
Ah, I see. So if the database developers introduce changes to the internal storage format in a newer version, maybe optimize how blocks are laid out.
Exactly. The format of the wall itself is likely to evolve along with those changes.
And how does this impact routine operations like, say, upgrades, which are pretty common?
Well, this tight coupling can have significant operational ramifications, especially when you're aiming for zero downtime upgrades. Ideally, you'd want to upgrade your follower nodes to a newer software version first, right?
Yeah, test them out.
Verify they're stable, then perform a failover to one of the upgraded nodes, making it the new leader. Smooth transition. However, with wall shipping, the replication protocol often doesn't support version mismatches between the leader and the followers.
Oh.
A follower running a newer version might not be able to correctly interpret the wall stream from an older leader, or vice versa. The formats might just be incompatible.
So rolling upgrades become very challenging.
Very challenging, and often necessitate downtime because you have to upgrade everything more or less simultaneously, or accept that replication will be broken during the process.
That's a crucial point to consider, especially in environments where continuous availability is paramount. Like 247 systems.
Absolutely.
So, while wall shipping offers incredibly strong consistency, but operating at such a fundamental level, it inherently restricts flexibility, particularly regarding software upgrades and the ability to run different database versions in a replication setup.
Exactly. That trade-off between consistency and operational flexibility is key here.
Okay.
Now, let's delve into a third strategy that aims to address this tight coupling. Logical, or sometimes called row-based, log replication.
Logical replication. Okay.
This method focuses on decoupling the replication log from the intricacies of the storage engine.
Okay, so instead of shipping the raw, low-level WOL, logical replication employs a different kind of log, one that describes data modifications at a higher level of abstraction.
That's the key difference.
Specifically at the level of individual rows within your tables.
That's the core idea. A logical log consists of a sequence of records, each detailing a specific row-level change.
Right.
For an insert operation, the log record would contain the new values for all the columns in the newly inserted row. Simple enough. For a delete, it needs sufficient information to uniquely identify the row that was deleted, typically the primary key. That's ideal.
Makes sense.
If a table lacks a primary key, which happens, it might need to log all the old column values to ensure the follower can find and delete the correct row.
A bit more verbose then.
Potentially, yeah. And for an UP date, the log would identify the row being updated, again, usually by primary key, and then record the new values for all the columns that were changed, or sometimes even the complete set of new column values for the row, depending on the specific implementation.
So if a single transaction modifies multiple rows, maybe across different tables, the logical log would contain a series of these row-level change records, followed by a commit record to indicate the transaction's completion.
Exactly. It groups changes by transaction.
I recall that MyC's binary log, the bin log, when configured in its row-based mode, functions pretty much like this.
Yes, the bin log in row-based mode is a prime example of logical replication. And the primary advantage here is that decoupling from the underlying storage engine.
Right, avoiding the wall issue.
Precisely. Because the logical log describes changes in terms of rows and their data, it's significantly easier to maintain backward compatibility between different database software versions. This often grants you more flexibility. You can potentially run different versions on the leader and the followers, allowing for those smoother rolling upgrades.
That directly addresses the big upgrade headache associated with wall shipping. Are there other notable benefits to this logical approach?
Absolutely. Another big one is integration. Because the logical log is essentially a structured stream of data modifications, like here's a row insert, here's an update. It becomes much simpler for external applications to parse and consume.
External applications like what?
Well, this opens up powerful possibilities for change data capture, or CDC.
CDC, right.
You can feed these logical log records into external systems. Think data warehouses for offline analysis, or maybe updating search indexes in real time, or maintaining external caches. It provides a cleaner, more abstract way for other parts of your system to understand and react to changes happening in your main database without needing to understand the database's internal storage format.
That sounds incredibly valuable, especially for microservices or just integrating different components in a complex architecture.
It really is. It fosters looser coupling between systems.
So logical replication offers enhanced flexibility, particularly for upgrades, and better integration capabilities compared to wall shipping, potentially at the expense of a larger log size sometimes.
That's a fair assessment, yeah. In some cases, especially with updates that change many columns frequently, the logical log might indeed be more verbose than the raw wall.
Okay.
But, the added flexibility, particularly around upgrades and interoperability with other systems like CDC consumers, often makes it a very compelling trade-off for many use cases.
Okay, so we've covered statement-based, wall shipping, and logical replication. Now, there's a fourth method mentioned, trigger-based replication. This sounds like it takes a completely different tack by involving application-level code.
It does indeed. Trigger-based replication essentially pushes the responsibility for capturing and replicating data changes up to the application layer within the database itself using database triggers.
Okay.
This provides a great deal of flexibility, but it also introduces more complexity and potential overhead.
How does that practically work? What are these triggers exactly in this context?
So in many relational database systems, you can define triggers. They're essentially custom code snippets, could be SQL, PL/SQL, etc., that are automatically executed when specific data modification events occur on a table, like an insert, update, or delete.
Right, I've used those.
Okay, so with trigger-based replication, you define a trigger that fires whenever a write operation happens on a particular table you want to replicate. This trigger code then logs the details of the change, maybe the old and new values of the row, what kind of operation it was, into a separate dedicated audit table or replication log table you create.
So the trigger acts as an interceptor, basically capturing the data changes as they happen and just writing them down somewhere else within the database.
Exactly. It records them in a structured way in another table.
Okay, but what mechanism then takes that log data from that custom table and replicates it to the follower systems?
Typically, that's handled by an external process or agent. This separate piece of software is responsible for periodically reading this custom log table.
Okay.
And because this logic is implemented partly at the application level using triggers and partly in this external process, you have very fine-grained control.
Control over what, specifically?
Over what data is read from the log table, how it might be transformed, filtered, and where it's ultimately replicated. This allows for highly customized replication scenarios.
Right.
Like replicating only a specific subset of columns, or maybe performing data transformations during the replication process, like anonymizing data, or even replicating data to a completely different type of database system, like from a relational DB to a NoSQL store.
Okay, I see.
Tools like Database for Oracle or Bucardo for Postgres are examples of systems that leverage this kind of trigger-based approach, often providing the framework and the external agent.
That level of control sounds powerful. For instance, if I only needed a read-only replica containing, say, just a few specific columns for some reporting dashboard, trigger-based replications could potentially facilitate that quite directly.
Exactly. It grants you very precise control over the replication flow, which the built-in methods might not offer as easily. However,
The inevitable but.
This flexibility comes at a cost. A key consideration is that trigger-based replication typically introduces higher overhead compared to the built-in replication mechanisms.
Why is that?
Well, you're essentially executing additional custom code, the trigger logic, with every single write operation to the source table. That adds latency and CPU load.
Right.
It's also generally more susceptible to bugs and limitations because, well, you're responsible for implementing and maintaining the replication logic yourself, both the trigger and the external process.
Yeah, you wrote the code.
You wrote it. You own it. You're not relying on the database vendor's highly optimized and thoroughly tested internal replication mechanisms.
So while it offers maximum adaptability for very specific, maybe complex replication requirements, you need to be really mindful of the potential performance impact on your primary database.
Definitely.
Due to the overhead of the triggers, plus the added complexity of managing all that custom replication logic. It sounds like it's most suitable for niche scenarios where the built-in methods just can't provide the necessary level of customization.
Precisely. It's a powerful tool, but probably not your first choice unless you have a very specific need.
Okay.
Finally, we should briefly touch upon a critical concept for ensuring data consistency in replicated systems, especially when failures happen.
The fencing.
Sometimes dramatically referred to as stoneth, shoot the other node in the head.
That's certainly a memorable acronym. What does it signify in the context of database replication?
That sounds
Aggressive.
It sounds aggressive, but it serves a vital purpose. Fencing is a mechanism for preventing data corruption and ensuring data consistency, particularly in failure scenarios where the primary leader database might become unavailable or unresponsive.
Okay.
The fundamental goal is to avoid a situation known as split brain.
Split brain. Yeah.
That's where two separate nodes in the replicated system mistakenly believe they are the active leader, maybe due to a network partition or something.
And if both start accepting rights?
Chaos. If both nodes start accepting write operations independently, it can lead to irreconcilable data inconsistencies and even data loss when the system tries to figure out what the true state is later.
Yeah, that sounds disastrous.
It is. Fencing aims to reliably prevent the old, potentially failed or isolated leader from causing any further damage or accepting any new rights once a new leader has been elected and taken over.
How does it do that? Like literally shutting it down?
It can involve various techniques, like using power control devices to forcibly reboot the old leader, disabling its network interfaces, or using special locking mechanisms. The key is ensuring it cannot act as a leader anymore. We can definitely dive deeper into the specific implementation details of fencing maybe in another session.
Okay.
But the main takeaway for now is that it's a non-negotiable component when designing truly resilient and reliable replicated database architectures. You need a reliable fencing mechanism.
Okay, that makes perfect sense.
Yeah.
It's the essential safeguard to prevent those dangerous split-brain scenarios and ensure that only one node is actively serving as the leader at any given time. A single source of truth.
Exactly.
So to quickly summarize, we've explored statement-based replication with its initial simplicity, but numerous potential consistency issues, especially with non-determinism.
Right.
Then wall shipping, offering strong, almost physical consistency, but with that tight coupling to the storage engine, making upgrades tricky. Then logical replication, providing greater flexibility, better upgrade paths, easier integration through CDC, potentially at the cost of larger logs.
Yep.
And finally, trigger-based replication, granting maximum control and customization, but bringing along higher overhead and the burden of custom code management.
That's an excellent summary of the core methods and their main trade-offs.
And fencing is the safety net.
And fencing as the crucial safety net for failover scenarios. For anyone preparing for that senior software engineer role, really internalizing the strengths and weaknesses of each of these is absolutely essential.
Yeah.
The choice of replication strategy has profound implications for data consistency, yes, but also operational complexity, those upgrade procedures we talked about, performance, and even how other applications within your ecosystem can interact with your database infrastructure.
Absolutely. It's clearly not just about knowing the names of these techniques. It's about deeply understanding the trade-offs involved and being able to articulate why one approach might be more suitable than another for a given set of requirements, the kind of reasoning expected at a senior level.
Precisely. And this brings us to a crucial point for you as someone prepping for that interview and for everyone else listening. Considering these various strategies, what do you think are the absolute most critical factors to weigh when selecting a replication method for, let's say, a high-throughput, globally distributed e-commerce platform?
Okay, high-throughput global.
Yeah, where both minimal latency and strong data consistency are paramount. And maybe add this. How would the necessity for frequent zero-downtime upgrades heavily influence your decision-making process?
Right.
These are the kinds of multifaceted questions that really test whether you understand the interplay of these factors, going far beyond just surface-level definitions. It's about applying the knowledge.
Definitely a lot to consider there. High traffic, global distribution, consistency needs, and smooth upgrades. It really underscores that selecting the right replication strategy isn't a one-size-fits-all decision and demands a really careful evaluation of numerous interacting factors. Thanks for providing such a thorough deep dive into the world of database replication.
My pleasure. It's fundamental stuff.
For those of you tuning in, I encourage you to continue exploring these concepts and to think critically about how they apply to the diverse software engineering challenges you might encounter. A strong foundation in these fundamentals is, well, indispensable for building truly robust and scalable systems.